This is a pulley. There's a mass hung from here. The mass of the is m3. There's another pulley m1 and from which mass m1 and m2 is hung. Okay, now the question is, the whole system is hung from a ceiling. The question is, what would be the relation between m1, m2 and m3 so that the block m3 remains stationary? I'm giving you 4 options for that, and you have to choose one among the 4. Okay, these are your 4 options. One is the right option. You have to choose the right option. The question is, what should be the relation between m1, m2 and m3 so that the mass m3 remains stationary? m1, m2 can remain stationary and they can move as well. But m3 has to remain stationary. That is the only condition that you have to fulfill. Okay, so try your hand on this. This is a relatively better problem. The right option is option number C. So many congratulations to those who have got this. And you feel very confident about it, then you may skip the discussion for this. M3 got to remain stationary, right? So net external force on M3 has to be 0. M3G is the force acting downward and the tension would be acting upward. So the condition that M3 has to remain stationary is that tension must be equal to M3G, right? So this tension is M3G. So this tension is M3G. It's a continuous string. There is no breakage. There is no knot. So the tension at this end will also be M3G. Now this is a uniform string, continuous string. So the tension in this string also be the same. So if we are calling it as T dash, then the tension here and here, if that is T dash, then this pulley, did I tell you that the pulley is massless? If I didn't, then it's my mistake. I should have told you that the pulley is massless. You know why? Because we believe in this F is equal to ma. If the mass of a system is 0 or if it is negligibly small, then very conveniently we can take the mass to be 0 and that makes the right hand side as 0. If the mass is 0, then there is no force required for any movement of that body. It will move with negligible amount of force. Because there will be no inertia. Inertia depends on mass, remember? So if the mass of a system is 0, or if we are taking it to be very, very light, then the net force on that system has to be 0. If mass is 0, right side is 0, then the force has to be 0. There will be no force required for the movement of the body. So pulley is massless. That I should have told you right at the beginning. I didn't. My apology. But now I'm telling you that this pulley is massless. If that is the case, then this tension T should be equal to 2T dash. We'll be able to make this equation only if the pulley is massless. That means the net force on this pulley has to be 0. So that was a powerful information that I should have given to you. But nevertheless, now the T will be equal to 2T dash. That means T dash should be equal to M3G upon 2. Okay? Okay. Now all we have to do is write the equation of motion for M1 and M2. Suppose the M1 and M2 are moving with any acceleration. That could be 0 as well or any value. That is not going to bother us because M3G is remaining stationary. That's all we have to fulfill. So suppose they are moving with any acceleration. So we have to just write the equation of motion. So suppose M1 is going up. Then the tension is pulling it up. Tension is M3G by 2. Downward force is M1G. This is the net external force upward. That should be equal to mass into acceleration. If M1 is going up, M2 is coming down. So M2G is the force downward minus m3g upon 2 is the force upward. This is the net external force that should be equal to mass into acceleration. Now to eliminate a, we got to divide equation 1 and 2, and when we do that we will get m2 m3 by 2 minus m1 m2 is equal to m1 m2 minus m1 m3 by 2. So m2 m3 m1 m3, so let's bring this on this side. So this would give us m2 m3 by 2 plus m1 m3 by 2 is equal to 2 times m1 m2, right? So this in turn becomes m2 m3 plus m1 m3 is equal to 4 times m1 m2. Now if you're going to divide the whole equation by m1 into m2 into m3, you're going to get here 1 upon m1 plus 1 upon m2 is equal to 4 upon m3, and I guess this was the option number C. Okay, so that's how you do. Actually you only have one equation in your hand, F is equal to ma, and you have to play around with it. That's it. Okay then, up till now we had more discussion on the string force, and a string was massless in all the cases. But now let's very quickly discuss, if the spring was to have mass, then how the analysis will be different. Suppose this is a string, a thick string, it is having some mass of m, and this is a block of the same mass, and a force F is pulling them to its right. Now the force F would be pulling them to its right. There will be some acceleration of the entire system. They'll all have same acceleration, and that would be force upon total mass. Now suppose this is of length L, and we are looking at tension at a distance L by 4 from the end where force is applied. Then if you have to look at tension at this point, then you've got to draw the FBD. This is what you're looking for, M, and this will be 3 by 4 M. Right? So tension will be pulling only this part. Whatever is lying behind it, the left, on its left. This is the job of tension, to pull this part with the required acceleration. Okay, so this tension doesn't have the load, doesn't have the job to pull the entire system to its right. It has a job to pull the system, whatever is lying towards its left. So if we write the equation of motion, this is the only external force for the system to its right, and this should be equal to mass. The total mass is 7 by 4 m, and the acceleration would be this. So the tension at this point will be 7 by 8 f. Tension will not be equal to the external force, and this you can very easily understand, because as you keep on moving left, the mass would be changing. So the job of the tension to pull the mass, that mass will keep on decreasing. At this end, it will have the lowest amount of mass, capital M. At this point, it will have the largest amount of mass, 2m. So at this point, the tension will be equal to capital F, and it will keep on decreasing because the mass is decreasing. Had the string been massless, then as you keep on going left, the mass is not going to change, so the required force has to remain the same. So the tension will remain the same. So the tension remains same only in case of massless string. If the string also has mass, then the tension will decrease as you go to the other end. Okay? Okay, then we'll just solve a very simple, easy problem based on the same concept. This is a thick string, mass m, length L. A force F is applied to it, and the whole string is moving. Now you have to tell me what is the tension as a function of x. X is a distance from the point where the force is applied. So tell me tension as a function of x. This is pretty goddamn easy. You find the tension as a function of x. X is the distance from the end the force is being applied. Find it out. Finding that is easy. You consider any point where you want to find the tension. Suppose this point we are considering. Draw the FBD for the rest of the thing. Rest of the thing would be L minus X, and this is the tension. Tension is pulling. This is only external force. Tension will be equal to mass. Mass will be mass per unit length into the length. M is the mass for the whole string, right? For this part, this will be the mass per unit length into the length. Into acceleration, acceleration will be F upon capital M. So tension would be F into 1 minus X upon L. When X is 0, then tension is equal to F. When X is L, you have reached to the other end, then tension is equal to 0 because there is no mass on the left hand side to be pulled. So tension at this end will be 0. So this is the expression for you. Okay. Okay, so now we have studied Newton's second law of motion and we have worked more on the strength force, and now we'll switch and study some of the cases where spring force will be involved.